Hey guys, this is Safety Systems and Regulators. I'm going to try to get through this kind of quickly because a lot of this we're going to cover in lab, and it will make more sense when you guys actually have the hands-on equipment there. Sorry, that's my puppy scratching the floor. Anyway, so I just put another slide in here showing the agencies that you guys are required to know. This is that alternating manifold again we talked about last time, the large liquid bulk storage with the reserve next to it, kind of reminding you guys of the risers and the zone valves, all stuff we're going to look at very specifically in lab. So just kind of touching on cylinder safety, we go to MRI with patients quite frequently. At times we have equipment that has metal. Oxygen tanks are a good example of that. And MRI is a giant magnet. So this is a video that kind of just shows what can happen if you take a tank into an MRI. No metal should go into an MRI, as well as the fact that the tank is pressurized up to 2200 psi. And so that also has issues with cylinder safety. So if you watch these two videos when you guys have time, basically what we're looking at here is, you know, tanks under heat or tanks that get knocked over, things like that can all become either explosive or projectile. They can like launch. So you guys can watch the videos. We'll talk more about it in lab. Continuing on here. Sorry, trying to find a place in my house where there's no dogs or kids tends to be pretty hard. So just a real quick refresher on the anatomy of the cylinder. We're only worried about H tanks, E tanks, and D tanks. These are obviously more listed here. This is the valve stem, which is just this area here located on the top of the tank. This is what it looks like on the larger tanks. On valve stems, you have safety systems that are designed to release pressure. You guys are going to be responsible for memorizing these safety systems. And basically what it does is as the temperature increases, pressure also increases. So there's these pressure relief valves. These are the three that you guys have to memorize. You have your frangible disc, which is going to be on your tanks above size E. It's going to rupture at 3000 psi to relieve that high gas pressure. You have spring-loaded valve, which is a little bit different, still located on tanks above size E. For this one, though, you can set a preset pressure, and it will vent the gas at that preset pressure. So then it doesn't just explode the disc out and release all the gas. It kind of allows a little bit of gas to release to keep reducing the pressure. Sometimes that will save your tank. You have a fusible plug, which is on E-tanks and smaller, and it melts at a specific temperature, and it opens the valve stem again to relieve that gas pressure so that it doesn't explode. When you store cylinders, you want to store them with the valve closed. So if this is your cylinder valve, this is your turn knob on the top. These are your smaller tanks, which has a turn knob here. You obviously want to make sure they're always closed. When you open them, you're going to open them fully, and then you do like a half turn back. When you open them fully and let them go, the gas coming out of the tank is very, very cold, and it can freeze. Again, these are things we're going to look at in lab, so I'm going to go kind of quickly through this. These are your regulators. These are what fit on top of the valve stem, and they serve two major functions. They reduce the pressure to a working pressure, and that working pressure is 50 psi, which we talked about previously, the number just to memorize. So it's going to take your full tank of 2200 psi, and it's going to take it down to a working pressure of 50 psi. So that's one of the things that it does. The second thing it does is it's got a flow meter that's going to control and indicate gas flow to your patients. So those are the two things that your regulator does: reduces your pressure to a working pressure and controls and indicates your gas flow. This is the inside of a reducing valve. Who's excited about that? You do not need to memorize that. You do not need to know that. It's just a visual in there. Cylinder safety. This is going to be a demonstration in class, so I'm just going to kind of squeeze right past this. We're going to talk about this in when we do our lab competency. So definitely know these things, but we'll talk about why in lab. So you have 3 safety systems, and I realized that in the PowerPoint I worded this strangely, so I did a second recording, and I will clarify on Friday when you guys finally get into Blackboard. But the 3 safety systems that you have in place by the Compressed Gas Agency are your American Standard Safety System. This is a safety system that uses different threadings to make sure that you can only attach one regulator. Like there's an oxygen regulator for an oxygen tank, a room air regulator for a room air tank. And the way that they make that possible is they change the threading so that you can't thread one onto another. And what this does is it's one way that it can prevent the wrong medication delivery. If you think about therapeutic gases as a medication, oxygen is a medication, you want to make sure you're not delivering the wrong medication. So this is one of the ways that you can ensure that you're delivering the right gas. So the American Standard Safety System, the way that I used to always remember this, because this is on tanks that are larger than E tanks. So this is basically your H tanks for your guys' purposes. Since that's the only one we're really focused on, I just always remember this as big ass tanks. Your PIN index safety system, that is going to be on your e-tanks and smaller. And the original PowerPoints I sent you guys in the email, I worded it very funny. So just know that the PIN index safety system is on e-tanks and smaller. I updated the PowerPoint, and when I get you guys on a Blackboard, the updated version will be worded correctly. So PIN index safety system, e-tanks and smaller. So this is where there's different pins located on the regulator. They only line up in a specific way. And again, you're just preventing connecting the wrong regulator to the wrong gas, thereby hopefully making it less likely that you would deliver the wrong gas to a patient. Your disc safety system, or diameter index safety system, is your low pressure connection. So less than 200 psi, which is also a number that you guys should have memorized. But these are going to be like your station outlets, which are what are your wall plugins, your respiratory equipment, your pressure reducing valve. All of these are your disconnections, and we're going to go through these in labs where you guys see some examples. So this is kind of a close-up of the American Standard Safety System. This is where the threading would be. Tanks larger than E. This is your PIN index safety system. It's kind of hard to tell from this picture, but basically there's like this PIN system. It only lines up one way. There's a table in Egan, and just for future reference for the boards and for my exams, memorize the PIN positions of oxygen and memorize the PIN positions of room air. It comes up. So those are the 2 that you're going to want to commit to memory. And this PIN index safety system is on your E-tanks and smaller. Your disconnection here, this is a couple of pictures of examples of the disconnection. Again, this is for low pressure. It's a low pressure safety system. So less than 200 psi is the threshold for that. So this is an example where you could see multiple safety systems on one tank. So this is your H tank. This is your ass connection there. Yep, I just said it. So this is going to be that threaded connection, right? And it'll only fit on, this is an oxygen regulator. This is only going to fit on an oxygen tank. This is your big ass tank. So that's how you know it's this guy. When you come over here onto the flow meter, because at this point, this is your reducing valve. It's reduced that pressure to that working pressure of 50. Well, now you have your flow meter with this low pressure of 50, and you have your disconnection, okay, down here. Here you have your PIN index safety system because this is an E tank. And then again, you have your disconnector here because this is now at 50 psi for your working pressure. Again, things we're going to look at in lab, but just to kind of give you guys a frame of reference. Again, station outlets are your disconnection or your quick connects. We'll talk about those. 2 flow meters that we're going to talk about in lab in detail is your board-on gauge and your Thorpe tube flow meters. That does not mean that these are the only kind of flow meters out there, but they're the most common and they're the only ones that you guys have to worry about. Obviously, when you get your guys' jobs out in the real world, they may have different things that you'll have to learn about at your facility. Big takeaways here. The board-on gauge is what we use for transport. So it's basically, here's your regulator, here's your pressure gauge, and then this whole thing is considered your board-on gauge right here. The variable pressure, you're not going to be quizzed on this because I personally find it slightly confusing. The working pressure coming out of this is 50. The reason that it says variable pressure is because there's some instances with medical transport where they will make that pressure adjustable and they will allow you to change the standard working pressure of 50 psi up to like 100 psi, and it has to do with the fact that some of the equipment has downstream resistance and they want to compensate for that. Not anything you guys have to worry about, not anything I'm going to test you guys about, but that is technically why it's considered a variable pressure. It's a fixed orifice outlet because right here where you would attach your O2 tubing, that is just the same diameter hole all the time. So it's fixed orifice. The big thing to remember about these is they can be used laying down in a bed or laying down in a tank holder, which is why we like them. They're not gravity dependent, but because of that, they're also not back pressure compensated. And what that means is if you hook tubing up here and you set your flow at 4, if your tubing down here by your patient gets kinked, nothing will tell you that. Your flow meter is still going to read 4. 4 is still going to be leaving this tank. You'll have no idea that your oxygen tubing is kinked until your patient starts to desat. So when we use these kinds of things for travel, it's really important to realize that if all of a sudden your patient is desatting or having an issue, follow your tubing back and make sure that it didn't disconnect, make sure that it's not kinked, because nothing on this gauge is going to tell you that there's a problem downstream because it's not back pressure compensated. Conversely, the other flow meter that we're going to talk about is the Thorpe tube flow meter, and this is the one that you guys have probably seen pretty commonly and even got a chance to use in clinical. So this is a fixed pressure. It's always attached to a 50 psi source and a variable orifice. And why that's different than your board-on gauge is here, and you can't really see it from the picture, but inside this Thorpe tube, there's a V shape. As you go up this glass tubing, it gets wider and wider. The column gets wider and wider and makes a V. And what that's doing is as you go up into higher flows, it allows for more room for that air to flow in. So that's what makes it a variable orifice. You always read the center of the float, which is that metal ball that's in there. You want the center of it to line up with whatever flow you're trying to create. So the two opposing forces that are utilized with the Thorpe flow meter are gas flow and gravity. So obviously gravity is pulling the ball down, gas flow is pushing it up, and like the relationship between the two is where you measure the center of the float to set your flow. The reason that this one can't be used like the board-on gauge for medical transport is if you lay your Thorpe tube flat, which you would do transporting a patient if you had your tank in the bed, the center float falls because now you don't have that gravity, you just have the flow, and so it doesn't read correctly. So this is considered back pressure compensated. So where this comes in handy is if you do have a patient that's hooked up to 4 liters, like you did in the other scenario, and the oxygen tubing gets kinked or gets disconnected, you're going to see that float fall. It's going to tell you that something is happening downstream. So that's an advantage to having a Thorpe tube versus the board-on gauge. Another way of saying it is what you see is what you get. If the equipment is attached to a patient, the tubing gets kinked, the center ball is going to fall. Okay, that gas flow will be gone and gravity will pull it down. So that is what it means by back pressure compensated. And that is the end. Like I said, most of that stuff we're going to go over in lab, so don't sweat that PowerPoint too much. It'll become clear when you guys actually get the hands-on.